Hello everyone, welcome to my presentation on the paper LIST Low Illumination Syntax Detector with Automatic Feature Enhancement. Today I would like to talk to you on the topic of text detection under low illumination, and I'm the presenter, Johan. As you can see, my presentation is divided into the following four parts: Introduction, Related Works, Methodology, Results and Analysis. Let me begin by giving you some background information about text detection and the introduction about text detection under low illumination. Text detection is widely used in daily life as shown in the first line of pictures, and has broad application prospects such as autonomous driving, assisted travel for the blind, and autonomous activities of robots. Although there is a rich literature dealing with a variety of challenges encountered in wide text detection, the performance degradation on low-light syntax image, as shown in the second line, is underexplored and not properly addressed. The first challenge is the lack of data scarcity. Currently, the only dataset for low-light text detection was proposed in 2020, which contains only 500 images, and it is obviously not enough. Another challenge for low-light text detection is the domain gap between different illumination, such as poor visibility, indistinct contrast, and severe noises of low-light images. Left figure illustrates the detection results with different methods and corresponding feature. In this figure, A is the detection result on low-light text image, and B is the detection result on the same image with pre-low-light enhancement. Compared with detection results of our method in C and the ground truth in D, existing detection models cannot effectively extract features, resulting in degradation of detection. Although low light enhancement could improve brightness to narrow the field gap caused by illumination, it also causes color deviation and noise amplification as shown in the right figure, which is not conducive to high-quality feature extraction. In this paper, we propose a low-light text detector based on automatic feature enhancement. For lack of low-light text detection data, we proposed a new dataset called doctext, with synthesizing low-light text image from existing text detection datasets. Finally, we conduct experiments on the proposed dataset and achieve state-of-the-art detection performance. Now, I'd like to move on to the second part of the presentation, related works. First, let me introduce current deep learning-based text detection methods. Current deep learning-based text detection methods can be divided into two types: coordinated regression-based methods and segmentation-based methods. CTPN is a classic text detection model based on coordinated regression. It combines fast RCNN with LSTM to locate text instances using sequenced candidate boxes. EAST is a detection model which is a mixture of the above two methods. EAST utilizes UNets to output the text segmentation map, coordinate regression map, and rotation angle map. DBNet is a segmentation-based text detection model which selects FPN structure as the detection head and neck, and outputs 3 single-channel maps for prediction of bounding box. Next, we will introduce work of text detection in the wild. This paper is proposed in 2020 and is the only work for low-light text detection currently. This model first enhances the low-light image and provides dense distributions for the feature, and finally improves the performance of low-light text detection. In addition, this model achieves good detection performance on the normal light text detection datasets. Finally, let me introduce some work of low-light enhancement. Enlightened is the first unpaired low-light enhancement model, which combines generative adversarial networks with low-light enhancement task. It utilizes unpaired normal light pictures in discriminator to provide reference information, thereby enhancing the illumination of low-light images. Their DCE is a non-referenced low-light enhancement algorithm, which enhance low-light images through multiple iterations of adjustments in pixel-wise and strong self-constraints. Next, I will introduce our low-light text detector and methods for synthesizing low-light images. First, let me introduce the synthesizing low-light images part. We reversely utilize the non-referenced low-light enhancement mode of their DCE. Formula 1 is the adjust process of each iteration in the enhancement. To darken images, we need to change the exposure loss function in their DCE as shown in Formula 2. M represents the number of non-overlapping local regions. Yk is the average intensity value of a local region in the synthesis image. E is the target exposure we need to change. Considering high-intensity regions, such as whiteboard, light source, we introduce a separation parameter beta in the iterative process and multiply it with second-to-last iteration results. Results of synthesizing low-light images is shown in this figure. Next part is the detection network of our detector. As shown in this figure, our detection network consists of 5 modules. A. Intensity adjusting model for image adjustment. B. Dual-pass feature extraction stone for feature extraction. C. Feature fusion branch for feature fusion and enhancement. D. Segmentation-based output layer. E. Fusion cell, which is embedded in C. Let me introduce the details and motivation of each model. Intensity adjusting model is referred as IAM. From the perspective of the neural network, the enhancement of brightness is not decisive factor for effective feature extraction. How to adjust the images? We think that this operation should be guided by the results of the detection side and beneficial to feature extraction. IAM shares the same network structure and the iterative process with the low-light synthesis part. The specific process is shown in Formula 1. After several rounds of iterations, we get an adjusted image. Motivation for dual-pass feature extraction stone is quite simple. We want to extract feature information as much as possible and provide sufficient information for subsequent feature fusion branch. You may be wondering why we choose dual pass rather than more pass. Actually, it is a compromise considering the computational burden. Feature fusion branch is designed for fuse feature information from dual pass. By strengthening the valid information and weakening the invalid information, we provide high quality features for the subsequent detection neck and head. Since determining the most suitable fusion network is time-consuming and labor-intensive, we choose an approach based on differentiable neural architecture search. For the specific search space settings, please refer to our paper. We select the detection neck and head from existing detection model, DBNet. In output layer, probability map represents the confidence of a certain pixel belongs to a text area, and the threshold map determines the threshold for probability map. And the final binary map is obtained by combining these two maps. Loss function is shown in this formula, and cross entropy loss is adopted for probability map and binary map, and L1 loss is selected for the threshold map. Visualization of text detection results of different methods on proposed dataset is shown in this figure. A and B is detection results of PSENet and PANnet. C, D, and E are detection results of existing detection methods with different enhancement methods. F is the detection result of our method. G is the ground truth. According to this figure, we found that existing detection methods have defects such as omission, false detection, and the coordinate deviation of the bounding box. Compared with other competitors, our method accurately localizes all text instances. Through low-light synthesis algorithm, we synthesize corresponding low-light version of existing text detection datasets. The text shape and data scarcity of these datasets vary in a large scale. This figure shows the detection results of our method on different synthetic low-light datasets, and our method also achieves great detection results. Here are the numerical results for all detection methods. On the proposed dataset, our method achieves the best precision recall at F-score with moderate computational cost. The synthetic low-light version of MLT 2019 has the largest data scarcity, and our method outperforms existing detection models in these datasets. We have carried out experiments on some popular normal light datasets. The first and second is the detection result, and the third and fourth slide is the corresponding ground truth. Although our method has not achieved state-of-the-art results, it shows that our method generalizes well on normal illumination images. Finally, I will explain the ablation study part. We verified the effectiveness of three key components: data expansion, which called DE with image synthesis, intensity adjustment model, which called IAM, in dual-pass feature extraction, and feature enhancement, which called FE, with fusion cell. Numerical results of different models are reported in this table, and DBNet serves as the baseline. As shown in this table, as shown in the first table, integrating IAM, FE, and DA in baseline model in sequence will gradually improve the detection performance. We also compare three different feature fusion methods and finally found that the feature enhancement method based on neural architecture search achieves the best detection performance according to the second table. Here, left figure is a visual comparison of different feature fusion schemes, and the right figure is the detection results with different feature extraction method and corresponding ground truth. Well, A is the detection results with single-pass feature extraction, and B is the detection results with dual-pass feature extraction, and C is the ground truth. Thank you for your attention.